Today we're looking at the use of OLEDs in model railways to enhance your layouts. OLEDs have become very popular over the years for good reasons, and you'll find them in many places in the real world, including TV screens, computer monitors, digital cameras and mobile phones, gaming consoles and Fitbits, and even in consoles in modern cars. Their increased use stems from their improved performance due to the materials used under construction. As you can see here, you don't use a backlight unlike their LCD equivalents, and you can see in the picture above me that makes them much thinner. Let's have another look. Here's a traditional LCD, here's the OLED. On the side of the LCD you can see the connections for the LEDs for the backlight, which isn't required on here. So if I hold them both edge to edge to compare, you can see just how much slimmer the OLED is compared to the LCD. And because they have no backlight, there's much less leakage, you get higher contrast, therefore they're clearer, you get a greater viewing angle, and importantly from our point of view, they take a lot less current than their LCD equivalents. On model railways, everything's in miniature, and thankfully OLED screens are available in small sizes for our purposes. We can use it in a simple mode, as here, a station display board, or we can have a much fuller implementation using several of these screens. There's an example of it in a recent Merck journal. Or there's Neil's implementation, where the content on the screen is dependent on input from train detectors. We could even contemplate using RFID so that the screen content depends on which train comes into the platform. Or outside the station we can have billboards like this, or like this, or like this. And here's one I just made up as a kind of example. Okay, we're interested, so where can we obtain these miniature OLEDs? Well, we can go down the commercial route. Train Tech do a product called the Smart Screen. As you can see there, it has a single board that you can program with your DCC command station. Fine, if you don't want to have any soldering or concerns, you can pay your £50. However, of course, if you're not a DCC user, you can't really use it. So, is there not some way we can make our own? Guess what? Yes. Fortunately, there are many sources for buying these OLEDs from eBay or AliExpress, Banggood and so on. They come in different sizes and types. The one I'm looking at just now is the SPI version. It needs more pins, runs a bit quicker than the I2C version, but for simplicity we're really looking at these. They only require 4 connections, and they come either, as you can see, the 128 by 32 pixels or 128 by 64 pixels. So 128 pixels in the horizontal direction and 64 vertically. And that's the ones we'll be looking at, the I2C versions. There's one of the smallest ones. It's only ½ an inch. You can buy them on eBay. This is the larger version, the 1 inch screen that we'll be looking at in more detail as we go on. But of course they don't work on their own, they have to be programmed and connected to make them do what they have to do. So, what are the hardware requirements? Well, you're looking at them. Just the screen and one, in this case, an Arduino Nano. That's it. No other components, no voltage regulators, capacitors, resistors, transistors, just 2 parts. If you can connect these 2 together and you can program the contents, that's all we require. So how do we connect them? Well, you can see there at the top we have a Nano. We have to put power onto the Nano, so we apply 12 volts, just from your standard 12 volt supply. We also have to power, of course, the OLED, and it takes a lower voltage, so we take 3.3 volts from the Nano. So 12 volts comes into the Nano, and it's got its own regulator built into it, and it supplies 3.3 volts to the OLED. No problems there because the OLED is a low current device, as you'll see shortly. So we now have both devices powered, and now we have to work out now is how do we send information from the Nano into the OLED. 2 more wires. One which is called the clock, which just synchronises data between the Nano and the OLED, and the other one is the data, the actual information that you want to display on the screen being sent from the Nano to the OLED. And there's a chart which shows just how little current the OLEDs actually take. This is for the 128 by 64, the 1 inch version. Commonly using a chip called the SSD1306. And if you use that, which is the most common one on these boards, you'll see just how little current. At its very maximum it's 20 milliamps, and that means when you have every single pixel on the screen illuminated, which isn't common. When the display's off, we've got as little as 26 microamps. When we're pure black, it's only ½ a milliamp, and everything in between. So generally speaking, you'll be pulling out maybe 8, 10, 12 milliamps depending on the screen content as it changes. So very low current, easily produced from the output of the Nano itself. I want to look now at 2 actual examples of the use of OLEDs on the layouts and demonstrations that we take to exhibitions. We have a showcase board that showcases the various pocket money kits and other kits that Merck produces. And at the next exhibition we'll be bringing out this additional demonstration. The top 4 are pocket money kits, but we wanted to look at how we program chips as well. So down the bottom we have on the right hand side the DF player. Press a button and you get audio, but on the left hand side we have the example of a nano controlling an OLED. And let's look at what that does. Our second example is taken from a up and down demonstration layout, which is well received. It shows. Only problem we had, you'll see there we've got a corner which is pretty bare, and it also exposes the catch. So we wanted to put something there, and we decided we'd have a cinema. So the first step was to move the three switches that you see there. Normally they're covered up by a vehicle, but they'd get in the way of the cinema, so they had to be rerouted and placed inside the building of the post office. And when that was done, we could make an animated sign for the cinema. Well, this is it. I just mounted it on the back, so that's only the width that will fit in happily inside the cinema. Right now I'm putting off 5 volts, but wires here to take it to the 12 volt supply. So I made up the OLED sign. Keith made that beautiful rendition of the Odeon cinema. Behind the scenes, not so pretty, we have the lights in the foyer coming through here. We've got a timer pocket money kit here, and we have a sequencer that will sequence the lights running up and down the fascia of the cinema that you'll see in a minute. And then we just have the OLED screen here. And the final product looks like this. I'm sure this will be well received at exhibitions. And the building itself and the extended wall at the back helps to cover up the ugly holding catch. And since this picture was taken, we have put up some more walling and items along this empty area too. So we've seen the hardware, 2 items. We've seen what it's capable of doing. The question now is, how do we make it work? And for that we're looking at software. I'm assuming that you know how to use the Arduino IDE to write or edit programs, but there are special add-ons that we require to write to the OLED. The additional code that we require are libraries, and if you haven't seen the video on how to install libraries, you'll find that in a previous video we created. Oh, there's lots of documentation online on how to do that. There are various libraries available. The one I'm using here is from Adafruit, and the first one is the SSD1306 library. As you'll see there, it's designed for the 128x64 and the 128x32, and it's used for basic screen commands such as text. And they also produce a GFX library, a graphics library, and if you add that into your code, it allows you to do various drawing of lines, boxes and shapes and so on, import bitmap images. So we have to install these two into the IDE before we do any other coding. The next step is to get the Arduino Nano to communicate with the OLED. And we have some basic setups that we have to perform. The first line of code, wire.h, is there to allow the Nano to talk to the OLED via I2C. And then we have our two other includes that we've already discussed. And then we have these lines to add in. The first one tells the Arduino that it's got to talk to that display with a 128x64 resolution, that it's using wire, it's using the I2C option rather than SPI, and the last value there is for a pin number if it was using SPI. The pin is used to reset the display if you're using SPI. We're not using SPI, so we're going to reset internally, so we don't allocate a pin number. -1 doesn't exist as a pin, and therefore we put that in there. And the second line has got two parameters. The last one tells you the I2C address of the OLED. You may know that all I2C devices have different addresses, and 3C is the address of the OLED. And the first parameter in there says that it's using its own internal voltage to supply the actual OLED panel. The OLED module is being fed by 3.3 volts, but the OLED panel that's used in it requires a higher voltage, something like 7 volts if I recall, and therefore if you put in that parameter, you're telling the panel to use its own internal charge pump circuitry to bump up the 3.3 to 7 volts to supply the OLED panel itself. And that's what it will look like. And now we're in a position to actually do some serious writing of text or graphics to the screen. At last, now we can at least look at putting some text on the screen. What do we need to do? All commands to the OLED from the nano, start with the word display. So the first command is to clear the display. If you give that command, then any content on the screen is removed and you're back to an empty blank screen. Always a good way to start the program. And then we can set the text size, and the N is a value between 1 and 8. So there's 8 different font sizes there. As you'll see in the small chart, size 1 means 7 by 10. That's like 7 pixels by 10 pixels for each character. 7 wide, 10 high. If you set the text size to 2, then it's 14 pixels by 20, and so on and so on. So we've cleared the display, we've set our text size, we then set the text colour. We only have 2 colours, black and white, so normally you'd be printing white on a black screen, although we could put black in the brackets to print black on a white screen. And then we have to decide where are we going to start. We don't have to have the text up the top left hand corner. It could be anywhere in the 128 by 64 pixel area. So how far along the x-axis do we go? How far down the y-axis do we go before we start the printing? And finally, we can print the text that we want. So we're going to print the characters at X and Y, the words "Hello World." We got there. Not quite, because the display print, or you can display print line, which gives you a carries your turn line feed at the end of the text. You jump to the next line, in other words. Doesn't in itself print it on the screen. What it's doing is setting up the bit image, all the nothings in ones, with the ones being the whites and the zeros being the black. All the pixels required to display Hello World. It's setting them up in the memory inside the OLED. And then once you set up in memory, you have the one final command, which is display the display. And at that point, all the contents of the screen memory inside the OLED are displayed on the screen itself. So there's an example of it. That piece of code puts everything together. We've put in our includes, we've set up the display, we've cleared the display and printed Hello World in white at 25.0. Right, so we finally got there. So let's look now at a few more text printing options. You can have what they call inverse text, where you set the colour with 2 parameters. If you set up the text colour with 2 parameters, you're saying that the text will be in black but on a white background. Or you can invert the entire display. If you say the invert display brackets true, then every pixel that was black becomes white and every white pixel becomes black. and then you can reverse it again by making it false. And if you had a for loop that kept on making it true, false with appropriate delays, then the whole screen would flash, which could be handy as a means of attracting your attention in any fault situation. When we're using it for instrumentation, for example, or automation or whatever. So that's how to print text. But what if we want to print values? Say we're having instrumentation and we're measuring voltage or temperature and so on. We want to display these, and they're going to be stored in variables. How do we tackle that? Let's assume we have a variable called val, and it's currently got a value of 78. In the real world it's been read from some kind of sensor, of course, but we'll assume it's now got a value of 78. We use display.print, and in the brackets we put the variable name val, and following that how we want to display it. So if you make it decimal, it'll display your normal 78. But if you make it hex, then it'll display the 78 as a hex value. And if we make it bin, we're going to get it displayed as a binary value. Depends what your end result that's required. We can also work with variables that have got decimal places using the float. So if the float says pi has a value of 3.1 blah blah blah, we can display it, as you see there, with the variable name followed by how many decimal places. If there's 0 decimal places, then it only displays the 3 from here. If it's got 2 there, it'll display 2 decimal places. And if it's got a 4, it'll display 4. But you'll notice it rounds the 5/8 up to a 6. So now we can display not only text, but numeric values. But you've noticed that the OLED display can show not just numeric and alphabetic values, but all various characters like dollar signs, colons, all that kind of stuff. How do we access them? Well, the character set is stored, it's changeable, but the standard set, the CP437, is the standard for the original IBM character set. So every character has got its own number, either decimal or expressed as a hex number. And you can see from that chart that you can access them in that way. So for example, if we were to access 3D, we would be printing an equals sign, whereas 3E would be a greater than symbol. So how do we do it? Well, we use a different command, display write this time instead of display print. And then you can do it decimal, so there you have it, display write number 3, you'll see at the top, is the heart symbol. Whereas decimal 24 is the up arrow, which is the same thing as hex 18. And if you do display write hex F8, you get the degree sign. So now we're able to print out the entire character set. The chip is configured to use the standard IBM font set. But if you've included the Adafruit graphics include, then you have access to other fonts. Let's have a look. Normal, italics, bold, bold italics, serifed, serifed italics, mono, mono bold. So how do we get them into our code? Well, you include them. You include the new fonts depending on how many you need. There's a couple of examples: the serif 9 point and the sans serif bold 9 point. You simply give that line and now you have access to that new font. Most of the fonts are available between 9 point to 24, 9, 12, 18, that kind of thing. But not every font type covers the entire range of point sizes. So once you've included the fonts, we can then use them at any point in the program by using the set font instruction. And you just pick the one you want. In this case we're using the serif font. So from then on all text will be displayed in the serif typeface. At any point you can revert back, of course, to the original IBM PC set by giving a set font with no parameters. Okay, so we're able to display text, the value of variables, various other characters, but what about the lines and boxes and rectangles and all that kind of stuff? How do we actually draw on the screen? At its simplest, we can draw one single pixel on the screen, just one little dot. We simply say how far along do we go from the left, how far down from the top, in other words the x, y coordinates, and in this case display a white pixel at that point. It could be display a black pixel if you had a white background. If you want to draw a line, you have to have two coordinates, your starting point and your finishing point. So x1, y1 is the origin of the line, x2 and y2 is the destination of the line, and again it can be white or black. But don't forget once again that they won't draw the lines, you have to use display.display before they'll appear on the screen. So simple dot or a simple line, but we can do other things. We can display rectangles. So once again, they're going to have 4 coordinates. The xy where they start and the xy where they finish. This time we're going to draw a box between them in white in the example. Or you have the option to make it a filled rectangle instead of just the outline. And again it'll be filled by white or black. And at the bottom we have one to draw a round rectangle. Now it's got 5 values. 4 for drawing the actual rectangle And the fifth one is how much rounding you want. If you made that a value of 5, we'd have less rounding. If you made it a value of 20, then the edges will be much more rounded. So that's rectangles. We can also draw circles, either the outline or a filled circle. The coordinates are your x, y, the centre of a circle, in other words, in this case 30, 30. And the value of 10 is the radius of the circle, and we're doing a white circle. And it could be an outline or it can be a filled circle. You'll notice at the bottom I've got 30, 30, 50. We've made the centre of the circle 30, 30, but made the radius larger than it can draw on the screen, so you only see part of the circle. And that could be handy in certain situations to get special effects. So that's that. Then we have the triangle, which has got 6 coordinates. So in this example we're going along 50 and down 20, and we're drawing a line to along 30 but down 40. And then we draw another line which is along 70 but down 40. And because you've told it it's a triangle, it'll draw the last line by itself. You don't have to give another set of coordinates back again. And it's going to be in white, either as an outline or as a filled triangle. And that's your set of drawing commands. That leaves just 2 more issues, some basic animation and adding images. Let's start with some simple animation. To get to grips with it, we have to realise that the memory map that the SSD1306 holds is a map of all the pixels that will display on the screen, all 128 by 64, but they're organised in what they call pages. So we have 128 across the way, 64 down the way, so page 0 will have 128 by 8. So will page 1, so will page 2, and so on. So each page holds a particular slot, if you like, of the total image. And when we write display.display, we're transferring all the contents of the memory stored in these pages onto the screen. All the dot pattern that's stored in memory ends up as the image on the screen. Knowing that, we can do some simple scrolling. The command that says scroll left has what page you want to start with and what page you want to stop with. So in this example, we're scrolling the entire screen, all 8 pages, page 0 to page 7. So they're all going to scroll until you say stop the scroll. It could scroll right, but we're looking at scroll left here. Another option is to only scroll the top half of the screen by saying go from 00 to 03. Just the first 4 pages get scrolled to the left. Or if I say scroll left from starting from 04 and going to 07, I'm going to scroll the bottom half of the screen. Or if I give it 2 and 5 as the parameters, the middle section. So we can leave most of the screen content on if we want and only scroll particular sections. Or we can scroll diagonally to the left or to the right. We've used that in the 2 of the demonstrations we showed you earlier. Another approach is that we know we can draw in black as well as white. So we can draw something in white and immediately draw black over it and it's gone again. As in this kind of example here. If we display, say, an object, a small object, and print it in white at a certain spot, wait a little while, and then immediately in the same XY coordinates draw the same object in black, it's gone again. And immediately draw the object slightly moved in white, wait a short while, redo it in black at the same coordinates. Then what happens is the object will move or appear to move between these new coordinates. And you can make it go in any kind of pattern you like. If you want to just increment and decrement, it can go horizontally, vertically, diagonally, or you can set a bunch of coordinates so it will follow a particular pattern. Another possibility is to have a loop where you display the object in white and then draw a black rectangle over that object and then redraw it in white again moved to a new position. Bear in mind though that I said earlier that the update speed on an OLED is not very fast. You're not going to get very smooth, very fast animations. But within that we can have a bit of fun. For example, the coffee cup in that cafe, we could quite happily have got those 3 lines there drawn in black and then draw them in white and then black moved on and back again so that the steam seems to shimmer. So we get an animated effect from simply drawing and redrawing black over white. Limited but still effective. Which brings us to the question of how do we add the graphic in the first place? The first step is to draw the image you want. Remember, we've only got 128 by 64 to play with. If we want to move the object, it can't be 128 by 64, it has to be quite smaller. And these 2 that you saw earlier were drawn in quite a small size. So we draw the image, usually save it as a bump file, BMP file. Step 2 is to take that same image and convert it into its binary pattern. In other words, what's going to be a black dot, a white dot, a white dot, a black dot and so on to fill in that graphic space. And once you've converted the image into its appropriate binary pattern of blacks and whites, we can paste that into the code of your IDE and it's available to be called up when required. The pixels that make up the image are stored in the code in that format as a series of bytes, each separated by a comma. And the image here shows you them in binary format where the 1s and the 0s represent the whites and the blacks respectively. So they can be stored in binary format that way, or they can be stored in hex. Either way, depends on which application generates the pixel pattern. So, what do we have to generate this from an image? One application is this one. It's free to use. You use it online. You import the image into the application, decide what's the black and what's to be white, and it generates the picture you see here. If you can half close your eyes and squint, you can probably see that that's the pattern for the loco. You can just see the cabin here and the body of the loco and the chimney. It generates the pattern that way. It's a bit of a faff because you've got to then convert that with commas to separate them out to add into the code. But it does show you the image. Another piece of software is the LCD Assistant, well used. Again, it's free. This time you download it onto your computer and use it as an app on your computer. Once again, you load the file in, and you can see from the preview what you've loaded, and you can decide the pattern. So it's chosen here to have 8 pixels in every byte, which is what we need, and we're going to generate the cafe image. Or there's image to CPP, which is also free to use and available online, where you can load in the image and you can manipulate it. I've got various settings here that allow you to determine the size of the image and whether you want to rotate it or flip it and so on. And then you can generate the code. And you can simply click here to copy the output and then paste it into your Arduino, into the IDE. If you want to show it, you simply say draw the bitmap at XY, where you want it to start, the top left hand corner of the image, what image you want to display. You have to tell it the width and height of the image you're using, and the colour, and then display it. There's an example. Display it at the coordinates 1214. It's a cup. It's 27 by 35 pixels, and I want to display it in white. So we've looked at the OLED and its hardware. We've looked at the range of instructions that the Nano can send to the OLED, and we've looked at some applications in model railways. Hope you found it useful, hope you found it interesting, but let's leave the last word to the OLED itself.